Thanks for the allowance. Thanks for the allowance.
You want some cheese to go with that wine? Oh! Look, if you don't want to run with the big dogs, don't come off the porch. You know what I'm saying? And many other stupid cliches I can come up with in the next 30 seconds. As we talked about yesterday, the squeeze theorem takes two functions and we squeeze another theorem in between it. And so our hypothesis again is that f has to be between g and x. And then when that happens, we get this puppy. If f is between g and h, for all values on the open interval containing c is our point that we're going to get close to, then this is going to be true. As h approaches some limit, which we call L, and g approaches some limit, which we call L, in other words, from the previous picture you see that they squeeze together to that same limit. When that happens, then the limit of f of x has to be the same. Does that make sense? Okay. Especially graphically, when you look at the picture, you can see h coming in, g coming in, approaching that limit value. If f has to stay in between them, f has to also approach the same thing. Okay? The question is, where are we ever going to use this? Which I wouldn't expect you to know the answer to that question. I was just going for a dramatic pause there. Before I show you the answer to that question, I have two theorems that you need to take a look at. They are those.
Sorry.
Okay, that's all right. I thought you're on fire or something. There's no, I have nothing clever for you on this. You just have to memorize these two things. They don't pop up very frequently. The first one with the sign pops up a lot more commonly than the second one.
That would probably be helpful to know.
Yeah.
Yeah, there were certain problems that you couldn't do.
You do them a lot.
Well, if you couldn't do a lot of them, that's your problem. If you couldn't do the ones involving those theorems, that was our problem because I didn't cover
There
this.
were some that just
Mr. Grass's problem,
don't you put that on yourself?
What's that, Taylor?
I said it was Mr. Grass's problem, don't you put that on yourself?
That's right. Thanks, man. I appreciate it. Good to know you got my back.
What's the first quiz on this?
I don't know, you have an assignment sheet.
Well, it's
You think I just typed
Test
those up for
Friday.
giggles?
It literally says
Okay.
pre-calc test Friday.
There you go.
Pre-calc.
Okay, so
Well, that's
if we look at the tangent of x over x, that's not one of the theorems. However, we can manipulate this quickly. Again, this isn't this earth-shatteringly important, so we're going to go through this pretty fast. I can rewrite the tangent as sine over cosine, which you're all well aware, and algebraically manipulate this tangent of x over x to look like this. Tangent of x over x. I'm attaching the x to the sine of x because I know a function for, or I know the limit for that. And then looking at the limit as x approaches 0 for 1 over cosine is pretty straightforward. What is the limit as x approaches 0 for 1 over cosine? 1. Correct, because you plug and chug, the cosine of 0 is 1, 1 over 1 is 1. And this you had on the previous slide. What's the limit as x approaches 0 of the sine of x over x? 1, and 1 times 1 is 1.
Wait. Why? Wait, wouldn't that cancel? Because there's a 0 on the bottom?
Put it on the unit circle.
Can I stop waiting?
Well, okay, but like,
It's the same thing as
It's
Just
sine
following
x
directions.
over x.
First thing you said was wait, so I
and
was
x
waiting.
is 0. Like,
sorry,
wait,
what?
because like, wait, I have a question. Okay.
Okay,
'Cause
so then
x-
I was waiting.
X is 0 and 0 is on the bottom, so wouldn't it like?
Correct, but the theorem overrules the whole 0 over 0 business.
So we just know that.
You just
whenever
gotta
we
know.
See that.
If you see sine of x over x, you just gotta know what that's equal to. Yeah.
And if you see 1 over cosine x, you gotta know it's 1. Or is that not?
That's not a theorem, that's just a plug and chug. Cosine
Oh.
of 0 is 1, 1 over 1 is 1. Okay, so we get that, which is, like we said, 1.
Because like on the homework we had last night, one of the example was the problem was it was the cosine theorem,
Right.
then it had like a 3 in front of it. So how would you do that? Put it in
Scalar multiple.
I dropped things out.
So the limit of a function times a number is the limit of the function times that. All right, Eric.
Not so bad.
Why does it work?
I don't know.
You know?
I mean, I could explain it to you, but it's gonna take too much time and I'd have to rethink it. That's why I said just memorize it. It doesn't, and I'm not a big, you know me, I'm not a big fan of pure memorization. In this case, it's easier to just memorize it than it is to go through the derivation of where that theorem comes from. Okay, to be honest, I can't do it off the cuff right now. And it's not important enough to spend the time doing it. Sure? Okay. All right, so nothing exciting here, but let's look at this buddy.
Where does he get the
What's it gonna do?
I was just confused on the last, like, I don't understand where you got the 1 over cosine x from.
This?
Yeah.
I wrote tangent of x as sine of x over cosine of x, all over x. And so I...
Oh, okay. I see.
Okay, good.
Yeah.
Glad I could help. I did nothing there, but that's okay. I have what's called a dampening function, and a dampening function is a function that as it approaches a number, it just keeps bouncing up and down. And we've said, way back when we talked about limits, we said that if you have an oscillating function, it doesn't have a limit. Because if I zoom in on this thing, it'll look exactly the way it looks now because this little function inside keeps bouncing up and down. This is that function. Okay, x squared times the sine of 1 over x squared. So if you look at it graphically, because it's an oscillating function, we shouldn't be able to take the limit. But we can use the sandwich theorem / squeeze theorem / pinching theorem to find the limit of this puppy as it approaches 0. Okay, so far? All right, so here's what we're going to do. You'll notice that that dampening function is sandwiched between two other functions. Those two functions are x squared and negative x squared. So I'm going to start with this. I'm going to take this warrants a little bit of discussion. I'm taking this simple statement, and hopefully you agree with me. The sine of t is always between 1 and negative 1. Yes? Right. You know what the sine graph looks like. It bounces up and down, but it's always between 1 and negative 1. And instead of t, I'm going to put in 1 over x squared. It doesn't matter what t is. You put anything into the sine function, the answer that you get out of it is always going to be between 1 and negative 1. So because I looked at the function, I want it to be 1 over x squared. So it stays between 1 and negative 1. Well, that still doesn't get me the function I want, so I then multiplied everything by x squared. That's a legal move. As long as you multiply it all by x squared, you're good to go. What that does for me is it sets up my sandwich theorem. It says that this function in the middle, that ugliness, is always going to be between x squared and negative x squared, which you can see from the picture there. Here's my dampening function. That's this thing, x squared times sine of 1 over x squared. And then here are my two functions that it's sandwiching in between. Okay, so all of that work, the only thing it does for me is sets up the sandwich theorem. And so the sandwich theorem says, if I can't find the limit of that thing, what do you got?
How would you know to change t to 1 over x squared if you were making the equation?
If you were doing this from scratch,
Yeah.
you would turn it into whatever it is you're taking the sine of.
But isn't that just the same thing as that?
What's that and that?
Well,
This
what's
is
the
just a
same
general
thing
statement.
then?
So
Okay.
this I just wanted to make sure that everybody understood that the sine of something is always between 1 and negative 1.
Okay.
And then I said, well, that something, for me, would work better if that something was 1 over x squared. So I slapped that in for x squared.
So you already had the equation when you were doing it.
Right.
So this is just to make the graph of it.
You got it.
Okay.
And you can put anything you want in there. You could take the sine of smiley faces. It's always going to be between 1 and negative 1.
Okay.
So I get that. Now the sandwich theorem says I'm not going to find the limit of the stuff in the middle. I'm going to find the limit of the top part, first piece of bread, find the limit of the second piece of bread. I got the limit then because this has to be the lunch meat in between the two pieces of bread. And no, we're not going down that lunch meat discussion again. Okay. So I got that. As the limit of as x approaches 0, then the limit of x squared would approach 0. That's a simple plug and chug. 0 squared is 0. The limit as x approaches 0 of negative x squared is also 0. So we satisfied the conditions that we need for the sandwich theorem. We know that the function that we're looking for is between the other two functions. We did that here. And then we look at the limit of the two pieces of bread. And since the limit of the two pieces of bread approach the same value of 0, that means that the limit of that lunch meat must also be 0.
How do you know that they're approaching 0? Is that just like, you know that from the graph?
Plug and chug.
Oh, okay.
Yeah. I literally took the limit as x approaches 0 of x squared and found that that's 0, and did the limit as x approaches 0 of negative x squared, and that equals 0 also. Pretty good with that?
Yeah, this
See.
might be a dumb question. I'm just
It's not a dumb question. The only dumb question is a question never asked. Which is a lie. There are some dumb questions. Hopefully this isn't one of them.
I hope not. I'm just like, when you're doing that whole sequence, I'm just confused where you get your -1 and 1 from.
Definition of sine.
Oh, right.
Sine and cosine are functions that always fall between 1 and -1 if you think of the graph. It just bounces up and down off into infinity.
Okay, I thought you got it from the graph.
No, I didn't, no.
Okay.
Okay, we good on the sandwich theorem? Not the most important theorem in the world, but it will help us find some limits when we deal with some really bizarre functions. The tricky part is this first part where you have to build your function. What you need to figure out is what functions denote the two pieces of bread. Once you find that, then the rest of it is pretty straightforward because you'll notice simple limits there with the two pieces of bread. Question?
What if the 2 on the other end, the limit's not the same? That just not.
Then you're done. You can't use the sandwich theorem. So if we go back to the picture, okay, still going back to the picture. A little bit, it's just, go there, right there. Okay. If I try to take the limit out here, it breaks down. So it's got to be that point where they have to approach the same value. They got to be smashing the bread down with the lunch meat in, and it's all coming to the same point. So if we go to that same problem and I took, let's say, the limit as x approaches 2, it falls apart. Because the limit of x squared and the limit of negative x squared are not the same thing. Okay, good question. Anything else? Outstanding. We're done with sandwich theorem. Let's stop this.